Chapter 3, Exercise 4. Find explicit expression for S2m. Find limits of subsequences S2m and S2m plus 1. Argue that the sequence Sn has only two subsequential limits. Consider the subsequence S2m. By definition, S2m plus 2 equals this. Since S2 equals this, we find that the following. These computations suggest that the explicit expression for S2m is the following. And continuing. Let us prove the later equality using induction on m. The base case m equals 1, S2 equals this. The induction step. Assume that S2m equals this. Then S2m plus 2 equals the following. So, for all m, S2m equals this. By theorem 320e, we have this. By theorem 3.3a, we have this. And we have this. We will show that half and 1 are the only subsequential limits of Sn. Consider a subsequence Sni that converges to S. Consider the case when Ni is even for infinitely many indices I. In this case, sequences Sni and S2m share the same subsequence that must converge to half, since this. So in this case, S equals half. In the opposite case, Ni is odd for all large enough I. Then sequences Sni and S2m plus 1 share the same subsequence that must converge to 1, since this. So, in this case, S equals 1. We have proved that the only subsequential limits of Sn are half and 1. This means that this and that. This exercise shows how one can get a sequence with several subsequential limits by combining several convergent sequences into one sequence. The obtained result can be generalized in the following way. Assume that this are real sequences such that this for every j in this. Define a new sequence Sn as follows. Then, the following are the only subsequential limits of Sn. We prove this statement by showing that each Sj is a subsequential limit of Sn, and that there are no other subsequential limits. Firstly, for any j in this, the sequence here is a subsequence of Sn, and Sj is a subsequential limit of Sn. Secondly, assume that S is a subsequential limit of Sn, and Sni is a subsequence of Sn that converges to S. For each I, divide Ni by this, where ki greater than or equal to 0 and ji element of this is a remainder. The range of sequence of remainders, ji, is finite. Hence, there is j in this such that ji equals j for infinitely many indices I. This means that Sni equals the following for infinitely many indices I. In particular, sequences Sni and Skj share the same subsequence that converges to Sj. So, S equals Sj. The behavior of the sequence Sn from exercise 4. Thanks for watching.